Alrighty. Morning, everybody. Welcome back to Calc 3. Let's be bad about that. I love that.
That was a great class.
Yeah, we love.
Oh, did you? I only heard a little bit of that. Anyways, good morning, everybody. Welcome back to Calc 3. Plan for today is we're going to finish up Standard 9 by talking a little bit more about derivative properties. With time towards the end of class, we will start Standard 10 and talk about the changes. Got office hours this afternoon from 2 to 3, tomorrow morning at 10:30, and tomorrow afternoon at 1 o'clock. As far as homework goes, Standard 9 is going to have a quiz on Friday. Just give you a sneak peek, kind of where we're heading. We'll do Standard 10 over the next couple of classes, probably finishing off sometime on Monday. And then we're supposed to have an exam after that. So you all can have a choice. Would you like an exam the Friday before spring break? Or wait until we get back from spring break?
Or what? After.
Let's put it to a vote. Who votes for before? 1, 2, 3. I'm not happy. Okay, good. 4, 5, 6, 7, 8, 9, 10, 11. 12. And after. The befores have it. Let me check out the other class, see what they have to say, and might be doing a exam 2 then before spring break. Okay, I just updated Blackboard, so everything on all your mastery should be now posted on Blackboard. If you think there's anything missing, please let me know. Does anybody have any questions or comments before we get started for today? What did the mathematical acorn say on the day that it grew up? On the day it grew up, it said, Gee, I'm a tree. Geometry. Anywho, last time we had started Standard 9, started talking about properties of the multivariable derivative. We kind of went through how the product quotient, sum and difference, constant multiple rules all kind of had multivariable analogs. And then we also talked about sort of these higher order partial derivatives, specifically looking at second order partial derivatives, where f sub xz, for instance, meant we took the partial derivative of f with respect to x, and then we took the partial derivative of that with respect to z, versus something like f sub yy means we just differentiated 2 times with respect to the same variable y. And we talked about how you could form a matrix out of the second order partial derivatives called the Hessian Matrix, where if you have a function f from Rn to R, you basically just make a matrix out of all of your second order partial derivatives, which will give an n by n matrix. And the question that we posed sort of at the end of last class is, does the order in which we differentiate matter? Because in the example that we saw, it looked like if we differentiated with respect to x and then z, it gave us the same as differentiating with respect to z and then x. And ditto with f sub xy, yx, f sub yz, zy. And the question we sort of posed at the end of last class is that always going to happen? And that's kind of what we're going to be focusing on for most of class today, is answering this question. So, start out, have some definitions for you. We're going to talk a lot today in class about what it means for a function to be of a class CK, which basically says something about how many times can we differentiate our function f before we start running into problems. So to start off with, we're going to be given a function f going from Rn to R. We're going to say that f is of class CK, where k is going to be some positive integer, k greater than or equal to 0, if all of the kth order partial derivatives of f both exist and are continuous over the domain of f. So in other words, suppose we have some function f going from Rn to R, and the kth order partial derivatives mean what happens if we differentiate k times. So this, for instance, would be a second order partial derivative. A third order partial derivative might look something like this, where we've differentiated 3 times. But if all of the kth order partial derivatives of f exist everywhere in the domain of f and are continuous, then we say that our function f is going to be of class C sub ck. So it's C. So for instance, if we were to say something like f is of class C1, what that would mean is that all of the first order partial derivatives, fx, fy, fz, and potentially more, depending on the dimension of your domain. How many inputs do you have in your input? How many components do you have in your input vectors? Sorry, it's turning out to be one of those days for me. If f is of class C1, then all of these need to both exist and be continuous everywhere f is defined. If f is of class C2, what that's going to mean is that all of these second order partial derivatives, fxx, fxy, fxz, fyz, etc., are all going to exist plus be continuous anywhere f is defined. And so on. We could talk about what it means for f to have class C3 with its third order partial derivatives, class C4, etc. We also are going to have a notion of C0 and C infinity, where we can say that if f is continuous everywhere it's defined, if f is a continuous function, then f is said to be of class C0. And finally, we can say if f has partial derivatives of all orders, exist and are continuous on the domain, then f is of class C infinity, or is called smooth. It's just another way to refer to that. So basically, this sort of class CK system basically gives us a way of telling how nicely behaved is your function going to be. Can we say it's continuous? Can we say its first order partial derivatives are nicely behaved? Can we say it's second order? If it's C infinity or smooth, that means we can keep taking partial derivatives forever. We will never get to a point where suddenly the function no longer exists or is undefined. So let's do an example where we kind of look at a function and see which of these classes is that function going to belong to. Because it is possible for a function to be more than one of these. And the function I want to look at is going to be the one we were looking at yesterday to start off with. F of xyz is x squared y plus y squared times z. And I want to ask which classes is this function going to lie in? So first of all, let's ask, is this going to be a C0 function? Meaning, is the function f of xyz equals x squared y plus y squared z going to be continuous everywhere that it's defined, meaning over all of R3? So what do y'all think? By a show of thumbs up for yes and thumbs down for no, is f here, this polynomial, going to be a continuous function? Seen a lot of thumbs up, and I agree. Because f is continuous over all of R3. Meaning, given at any point in R3, we could find the limit of this function as x, y, z approaches that point by just plugging in that point into the function. The limit's always going to exist, and it's going to be equal to the value of the function everywhere in R3. It's a polynomial. Polynomials are always going to be continuous everywhere. How about C1? Well, we had our first order partial derivatives of f sub x is 2xy, f sub y is x squared plus 2yz, and f sub z, which is just y squared. If f is of class C1, that's equivalent to saying these three functions are both going to be defined and continuous over all of R3. These three polynomials. So by a show of thumbs, thumbs up for yes, thumbs down for no, is f going to be of class C1, meaning these are all going to be defined and continuous everywhere. A little bit of hesitation going on, but it turns out it is. F is of class C1, with the reason being fx, fy, and fz are all defined plus continuous over all of our. So already we can see that our function f is going to lie to multiple classes. It's like a Hillsdale student. It's going to be taking classes out the wazoo. Meaning it can be both C0 and C1 at the same time. How about C2? So for C2, we need the second order partial derivatives, which are going to be 2y for fxx, fxy we saw was 2x, f sub xz we said is 0, because this is a constant with respect to z. Yx is 2x, yy is 2z, f sub yz is going to be 2y, f sub zx is 0, zy is 2y, and zz came up to 0. Thumbs up or thumbs down? Are all of these functions, all 9 of these second order partial derivatives, going to be defined and continuous over all of R3? Or does anybody think that there's a point? Or does anybody think that one of these is not going to be defined or continuous somewhere? Jacob, what are your thoughts?
I think it's good.
You think it's good? Yeah, these are all pretty nice. They're all either 0 or just multiply a variable by 2. I would say all of these are going to be defined and continuous everywhere. So this is going to be a C2 function as well. So here's the real kicker. Could we keep taking partial derivatives forever? And are they always going to be defined and continuous? Meaning, is this going to be one of these so-called smooth functions? Katie, what are your thoughts?
I think that they'll stay in this form or go to 0 forever and ever. So I would say that it's infinitely continuous, or I don't know how you say it.
Just of class C infinity.
Yeah, C.
Yeah, or infinitely differentiable would be another way to describe it. So, yeah, if we look at these 9 functions, if we were to keep differentiating, well, if we were to differentiate any of them 2 more times, we're going to just keep ending up at 0. And so the question is, let's write this over here. Is the function that takes in x, y, and z and just spits out 0, is that going to be a continuous function? Because if we keep differentiating, they're all going to end up at this point eventually. So what do y'all think? Is the 0 function? Yeah, Jacob?
I mean, it should be, right? Like, at f of any value is going to be 0, and as we approach any value, it's going to be 0.
Yeah, the limit of this function as x, y, z approaches any point in R3 is definitely going to be 0, because it's 0 everywhere, which means the limit will always be equal to the value of the function. So I would say this is going to be continuous. And even if we get to the point where we're asking, all right, I have like 900 of these fifth-order partial derivatives, and they're all the 0 function, well, those are all going to be continuous. So I think I agree with both Jacob and Katie here. This is going to be a C infinity function. And because it's C infinity, that automatically means it's also going to be C3, C4, C5, C6, etc. Don't play with C4, by the way. It'll blow you up. So this one, f of f, and by the way, this is going to be true of any polynomial. Anything where it's just positive integer powers of x, y, and z added and multiplied together. Any polynomial is always going to be C infinity. Because you can just keep taking derivatives, you're just going to keep getting more polynomials, eventually they'll all be 0. But polynomials, including the 0 function, are always going to be continuous and nicely behaved everywhere. No matter how many times you differentiate. Any questions or comments? So let's look at a more interesting one. So that one, we could differentiate forever without running into any issues. But the other function I want to look at is going to be g of x comma y. So this is going to be a function from R2 to R. G of xy is equal to x times the absolute value of y. And I want to pull down the screen so we can look at that for just a second. Everyone have that written down? What the heck? There we go. I can technology. I went ahead and graph this function. So this is g of xy equals x times the absolute value of y. Which, if we look at the function, it sort of looks like a TIE fighter to me. But a TIE fighter that's sort of slanted, so to speak. So we have a function that's going to be shaped like this. Sort of for positive values of x, it's kind of got this V shape, and for negative values of x, it's going to have this sort of upside down V shape. What do y'all think about this one? So first of all, would you say that this function g is going to be C0 from looking at the graph? Does it look like it's going to be continuous? Meaning, at any point, we could just find the limit by plugging in that point, x comma y, into the function? Show of thumbs, yay or nay? Let's see, lots of thumbs up. Katie, why a thumbs down?
It looks like I know this is weird, but from right and left, the limits are approaching different values.
Like along, like...
Or I'm sorry, no,
The
I'm
X is-
sorry, no, I'm already thinking that you can't differentiate it. Okay, no, never mind.
Okay, yeah, you're already thinking of C. So you're basically saying no to C1 in advance.
Yes, but yeah, I didn't realize that was what I was thinking, so.
And for C0, we're not talking about derivatives at all. So quarters are not necessarily a bad thing yet. But is this a continuous function? I would agree and say yes. This is going to be a C0 function because g of xy is going to be continuous over all of R2. Just like if we were to take a look at the original function f of x equals absolute value of x, that's also going to be continuous over the real numbers. At any point, including at 0, where we have this sharp corner, we could take the limit of the absolute value function, and it's just going to spit back what you would get if you plug that number into the absolute value, even at x equals 0. Limit as x goes to 0 of this function equals 0. Limit as x comma y approaches any point of x times absolute value of y is just going to be the function evaluated at that point. So we do get a C0 function. How about C1? Well, let's first of all look at the original f of x equals absolute value of x function. Is that function going to be something we can take the first derivative of at all possible values of x? Jackson?
You have to make it a piecewise function.
Oh, we have to make it a piecewise function. Okay, so what would the pieces look like for this?
Y equals x for x greater than or equal to 0, and y equals negative x for x less than or equal to 0.
Oh, you just want to write the original function that way. Yeah, you could do that. You could say just f of x by itself is x for x greater than or equal to 0, negative x for x less than 0. So how would we be able to differentiate that? So it would be 1 where and negative 1 where?
1 for x greater than or equal to 0.
And negative 1 for x less than 0? Does everyone agree with it? That we get a slope of 1 at every point, every x greater than or equal to 0, and negative 1 for all x less than 0? Jackson, do you disagree with your statement?
Yeah, not equal to 0.
Turns out this is differentiable everywhere other than at x equals 0. But it is not differentiable at 0 because the slope from the left is not equal to the slope coming from the right. From the left, we're getting a slope of negative 1. From the right, we're getting a slope of positive 1. And so this function, f prime of 0, I would say does not exist. It has a corner there. It's spiky. And if there's one thing you should remember from Calc 1, it's that spiky things are bad. Or maybe from growing up as a kid playing Sonic the Hedgehog games. So the original absolute value function, f of x equals absolute value of x, turned out to not be differentiable at 0. So what about the multivariable one? G of xy equals x times the absolute value of y. Is that going to be a C1 function, do you think? Thumbs up for yes, this is C1, meaning all the partial derivatives are going to exist and be nicely behaved everywhere. Or thumbs down for nope, this is not going to be a C1 function. Interesting. Katie, I notice you've gone back to saying thumbs up for this now.
Well, now I realize that f prime of 0 doesn't exist, so it's not really in the domain at that point.
Ah, it's not in the domain. 0 is not in the domain of f prime.
Yeah.
Is 0 in the domain of the original function f?
So, okay, so we're still looking at f at that point, but as in, it
Yeah.
has to, it doesn't, we're not changing what graph we're looking at after that.
Yeah, so I've erased it now, but if you look back at our definition of CK, we say it's CK if all the k order partial derivatives of f exist and are continuous everywhere in the domain of the original function f.
Gotcha.
Not necessarily f prime or the partial derivatives of f, but anywhere. But if this function was C1, then we would have to say anywhere that it's defined, the original function, which means everywhere in R2, this function would have to fail to be, or this function would have to be differentiable. Meaning, we could take partial derivatives, they would exist at every point in R2 and be continuous at every point in R2. So I noticed a lot of thumbs down looking around. Rana, why did you vote for thumbs down for this function being C1?
Because if we try to take the partial derivatives of with respect to x and respect to y, we would run into the same problem as when we were taking f prime of the f function.
Okay, so you think both of our partial derivatives would go haywire here?
I think the first one would be fine if you use the absolute value of y as a constant.
Yeah, so in other words, if we're taking our partial derivative just with respect to x, we would just get constant times x, and so just absolute value of y would check out, you think? This is a function of x, y. I think this one would be okay, because that's going to be defined and continuous everywhere in R2. It's the absolute value of y function. I think the problem, I think I agree with you, Brianna, I think the issue here is going to come out when we take f sub y. If we try and differentiate this with respect to y. So, can anybody think of any points in 3 dimensions, just from looking at the graph, where it looks like if we were to take a partial derivative with respect to y, meaning a partial derivative, meaning a slope going in the positive y direction, are there any points at which it looks like our function is gonna have an undefined slope? Trying to spin this around a little bit so you can get a sense of what the graph looks like. Where does it look like we're not going to be able to take a slope in the y direction? There? At the origin? Actually, I think the origin checks out. Because if you look carefully at the graph, it's going to be completely flat going in the y direction at the origin.
I thought that it was just the software that just...
Yeah, sometimes it's hard to tell, like, how does the software differ from what's actually going on. But actually, at 0, 0, it is actually going to be okay. Because, let me graph this. So, if x of t is t, y of t is 0. C of t is 0. Oh, shoot, wrong direction. That one's 0. That one's t. And let's make this bigger so everybody can see it. 6. Here's what I would say is happening at the origin. If we were to travel in the positive y direction to the left or to the right, it's just going to be a flat slope. And it's just going to be a slope of 0. So the origin, 0, 0 itself, I think, is actually going to be a point at which f sub y is defined. Can anybody think of any points, though, other than the origin at which it looks like our slope is not going to be the same, say, coming from the left and coming from the right? Emily? At y equals 0? At y equals 0, x equals what? Or just everywhere along the line y equals 0, would you say?
Yeah, everywhere.
This one's actually sneaky. And because it turns out any point where the y coordinate is 0, this function f sub y is going to fail to be defined. except at the origin. The origin's the only point along that line where we can take our partial derivative f sub y and get something that will give us a nice output. But if we were to sort of try and take along any other direction, or let's see, y of t is t, x of t is, say, let's say 1, t divided by t. Nope, that's not what I wanted. I think it's just that. Yeah. Let's say we were looking at the point where x is positive 1, y is 0. That's going to be a point where our partial derivative with respect to y is going to be undefined. For pretty much the same reason why the absolute value of x function has an undefined slope at x equals 0. It's because there's sort of this V shape where the slope coming from the left to the slope, well, technically this is backwards, so this is the slope going to the left versus the slope going to the right at that point, x equals 1, y equals 0. Those two slopes are not going to be the same. So let's see if we can actually go through and prove that algebraically rather than just looking at a graph. But yes? Of course.
So it doesn't look like the middle piece is along the x-axis. Is there
I would say that's along the x-axis, sort of this middle strip here. It's along the line where y is equal to 0.
Okay, but it looks like there's a gap between the x-axis and the
Like there's this sort of little flat strip in here,
well, so like when you're looking at it from the other angle,
like this.
yeah. You see there's like a gap between the x-axis and the
So like a gap like between here and here.
right.
That's going to be an issue related to the program's not accurately kind of graphing what's going on with the function. Let's see, if we wanted to, let's go back to this one for a second. If we wanted to make a slightly more accurate graph, we'd increase the number of grid lines. And basically, the bigger you make this number, the closer it's going to actually make the graph to what's actually going on. I'm not going to make it any bigger than this because it also causes the program to kind of lag, as you can sort of see, if you make that really big. But that would be a case where if this graph on the screen was perfectly representing what was going on, it wouldn't necessarily be an issue. But there's issues here just caused by the fact that the software can't do it perfectly. Good question. I'm glad you asked. So let's see if we can show algebraically that our partial derivative of f with respect to y does not exist at the origin. Or not the origin, just that it does exist at the origin. At 1, 0. So if we were to take the partial derivative of f with respect to y at 1, 0, which if you prefer you could write as del f del y at 1, 0, means the same thing. Unfortunately, since we don't have a nice sort of power rule formula thing to help us find the derivative, we would either have to do what Jackson suggested earlier, which is write this as a piecewise function, which I kind of don't want to do. Or we could go back and use the limit definition of how we take the partial derivative with respect to y. We take a limit as h goes to 0 of f of 1, 0 plus h minus f of 1, 0 all over h. That's how we define the partial derivative with respect to y at a point, is we take f of 1, 0 minus f of 1, 0, but we add an h to the y coordinate of the first one of these. If it was f sub x, we take f of 1 plus h, 0 instead. And then when we subtract these, divide by h, take a limit as h goes to 0, that'll give us our partial derivative of f with respect to y. So in other words, it's going to give us a limit as h goes to 0 of f of 1 comma h minus f of 1 comma 0 all divided by h. So first of all, what do we get if, I keep saying f, I mean g. Where g is the original function, g of xy is x times absolute value of y. If we were to plug 1 comma h into our original function, meaning we plugged in 1 for x and h for y into the original g of xy formula, what would that give us? In other words, I just want to evaluate this expression right now. If g of x comma y is x times the absolute value of y, what would g of 1 comma h come out to? Yeah?
The absolute value of h.
Yeah, it would be 1 times the absolute value of h, which is just going to be h, or absolute value of h. So this is going to give us 1 times the absolute value of h. How about g of 1 comma 0? Well, it's going to give us 1 times the absolute value of 0, which is going to be 0. So minus 1 times absolute value of 0, which when we simplify, 1 times absolute value of h minus 1 times absolute value of 0 all over h is going to simplify down to just absolute value of h over h. And now we have a Calc 1 type limit. As h goes to 0, what's going to happen to absolute value of h divided by h? I'll give you a hint. I'll write this as a piecewise function. It's going to be h over h if h is positive. It's going to be negative h over h if h is negative, because that's how the absolute value works. For a positive h, it just spits back out h. For a negative h, it spits out, well, the positive version, which will be negative h. So if the limit as h approaches 0 from the right comes out to be 1, and if the limit as h approaches 0 from the left of this expression comes out to negative 1, what's going to be the limit as h goes to 0 of absolute value of h over h? If it's always going to be 1 to the right of 0, it's always going to be negative 1 to the left of 0. Yeah?
Does not exist.
Does not exist. Which I think is what we wanted to show. We wanted to show that del g del y, or g sub y, the partial derivative of g with respect to y at 1 comma 0 was undefined. So, partial derivative of f with respect to x was cool. It works everywhere. That's defined. Absolute value y is defined and continuous over all of R2. But f sub y, the first order partial derivative of f with respect to y, does not exist at the point 1 comma 0. And so let's go back and ask the question one more time. Is g of xy going to be C1 or not C1? It's like everybody's showing a thumbs down, and I would agree. Because 1 comma 0, I would say g of xy is not C1 because g sub, I keep calling it f when I mean g. Pro tip, if you're ever teaching a math class and you want to refer back to an example over the course of an entire class, just call it f. It'll be easier to remember that way. But the partial derivative of g with respect to y of 1, 0 does not exist, yet 1, 0 is in the domain of the original function g. We could take g of 1 comma 0. That would just give us 1 times absolute value of 0, which is 0. So 1, 0 is in the domain of the original g, but it is not in the domain of g sub y. It's a point at which our partial derivative with respect to y did not exist. By the way, Gary, the reason why this would have checked out at 0, comma 0 is because if we had plugged in, if we had done this at 0, 0 instead of 1, 0, this would have ended up being 0 times absolute value of h over h, and the limit would have just come out to 0. We would have had this problematic absolute value of h over h thing going on, but since we're multiplying it by 0, it doesn't actually end up being an issue there. So g of xy turns out to be a function that is C0, it's continuous everywhere, but it's not C1, because we have a point, 1 comma 0, that is in the domain of the original function, but is not a point at which g of xy, or which the partial derivative with respect to y is going to exist. Any questions or comments about that? So by the way, I'm not even going to bother asking about C2 onwards because of a slick little theorem that we're going to look at. Where the theorem, in this one, I forgot to write down in the packet, so you're going to have to add this one yourself, even if you're just following along in the packet. It's going to say that if f is of class CK, then f must also be of class Cn for any n less than or equal to k. Basically saying if you know a class that f is, it automatically has to be everything less than that as well. So for instance, if f is of class, let's say, C3, what other classes would it have to be, according to this theorem? Oh? Yeah. F has to be class C0, C1, and C2 as well. What about C4? Did we say anything about whether or not, if f is of class C3, can we say anything about if f has to be class C4 or not? Matt?
3 is not less than, or 4 is not less than 3.
3 is less than 4, but 4 is not less than 3. So we can't necessarily say if it's C4 or not. It could be, if we're looking at a function like this, where f is C everything, it could be C4. Or we could have something like this going on, where it's one class, but not the next class down the line. And by the way, this is basically a generalization of the Calc 1 theorem that says if you have a differentiable function, it also has to be continuous. For a Calc 1 function, that's the same as saying if f is C1, then it also has to be C0. If it's differentiable, then it has to be continuous. This is sort of generalizing that and basically saying if you have all of your kth order partial derivatives that exist and are continuous, so let's say if all of our third order partial derivatives exist and are continuous, then the first and second order partial derivatives also have to exist and be nicely related. Any questions or comments about that result? But I gotta prove this because this is really hard to prove. So Dr. Burstel, why are you bringing up all this CK stuff? I thought we were asking about the question of does the order in which we take our partial derivatives matter? Does g sub xy equal g sub yx? Well, the next theorem, and this one is in the packet, is going to tell us what is the relationship between the class of a function, or the classes of a function, and sort of being able to swap around its partial derivatives. And what that theorem is going to say oops, that's not the right packet. What the theorem is going to say, I promise, I'll tell you, is that if f from Rn to R is of class Ck, then the order in which we take kth order partial derivatives, any kth order partial derivatives doesn't matter and will always lead to the same result. So for example, we could say something like if f is class C2, then that means we could take second order partial derivatives and any order, and as long as we're taking the same derivatives, the order doesn't matter in which we're going to take them. So for instance, f sub xy would have to be equal to f sub yx. Because according to the theorem, if it's of class C2, then our second order partial derivatives, the order in which we take them doesn't matter. If we differentiate with respect to x and then y, we'll get the same thing as if we differentiate with respect to y and then x. Yeah, sir?
Is this related to that weird transpose property?
It is, and we're going to come back to that here in a few minutes. That's actually going to be a corollary. That's actually going to be what's called a corollary to this theorem. If we were to take f sub, let's say yz, that's going to be the same as f sub zy. Because C2 means second order derivatives, we can take it any order, they'll always have to be the same. So let's say we knew, for instance, that f was of class C3. What would be some expression, according to this theorem, that would have to be equal to f sub yzy, where we differentiated with respect to y, and then z, and then with respect to y again? If we have a C3 function, we should be able to come up with a couple other third-order partial derivatives that should be equal to this. Anybody think of one? Yeah, what?
F sub z y y.
Yeah, f sub zyy. So you basically swap the first two. But in either case, we've taken the partial derivative with respect to y twice and z once. So according to this theorem, if you differentiate with respect to y twice and z once, if you have a C3 function, the order in which you're doing it doesn't matter. What else should be equal to these two expressions? There? Yeah, YYZ. That would kind of be another way to take the derivative with respect to y twice and z once. Is to just do the two y's at first and then the z. If you have a C3 function, all of these should be equal. How about yzz? If we differentiated with respect to y and then z, would that have to be equal to the first three? No?
No.
Why not?
Because it's z twice and not once.
Yeah. Even if it's the same variables, if you're differentiating a different number of times with respect to the same variables, as a general statement, since this one is y once and z twice, they don't have to give the same thing. In order for the theorem to kick in and say the order in which we take them doesn't matter, the total number of times we differentiate with respect to each variable has to be the same. In this case, if we're differentiating with respect to y twice and z once, it doesn't matter the order in which we do it, but it is going to be different if we're suddenly changing it up, and so now we're differentiating with respect to y once and z twice. So, I say generally because it's possible you can find a few individual functions where these are going to be equal, but they generally are not going to be. They don't have to be. Whereas for a C3 function, all of these are always going to be the same. So, is the order going to matter? Generally, it doesn't if your function is of the appropriate class. But if you were to have a function that's not C3, then it is possible for this expression and this expression to come out to something different. If, let's say, you had a C2 function, a class C2 function only, then those might not come out to the same. So, Sarah, you were asking just a minute ago, how does this relate back to sort of this property of the Hessian matrix, where if you take the transpose, it doesn't change? Well, that's actually going to be kind of a direct consequence of this theorem. We're going to call it a corollary, actually. I'm going to say we have a corollary where if f from Rn to R is of class C2, specifically, then the Hessian matrix is going to be equal to its own transpose. Where the Hessian matrix, again, was this matrix of second-order partial derivatives. fx1x1, fx2x1, fxnx1, fx1x2, fx1xn. This matrix of second-order partial derivatives, if we were to take its transpose, if f is a C2 function, then they would have to be equal. So why is that? Why specifically f being of class C2 is going to make it so this matrix, the Hessian matrix, is always going to be equal to its own transpose? Jackson?
It'd be hard to display one of C3 because with three variables, it would be hard to put it in going two directions.
It's true. It would be hard to kind of try to do a matrix of third-order partial derivatives. But we could certainly have a function from Rn to R that is of class C3 and still talk about its second-order partial derivatives. Like the polynomial function we looked at earlier, that was a class C2. Sarah, do you say something?
I was just going to ask whether it would still be fine if it was, say, class C3, but the Hessian matrix was still class C2.
Well, you wouldn't say the matrix has a particular class. It's only the function itself that has class C2 or not. I would say if f has class C3, then by the theorem that used to be here that I erased, it would have to be a class C2 as well, and so this would still check out. So this works really, as long as it's of any class greater than or equal to C2, it will automatically have to be C2 as well. But the reason why this result has to be true from this theorem is if we have something that's of class C2, then we know things like fxy and fyx will have to be. Or in other words, fx1x2 will have to be equal to fx2x1. If we were to take the transpose, where suddenly we flip-flopped our rows and columns, if you look at the structure of how this matrix works, as long as we end up with a general formula like fxixj equals fxjxi, which we would have for a C2 function, according to the theorem, if we were to take the transpose and kind of flip-flop the rows and columns, it would lead to the exact same thing. Because basically you'd end up with fx1x2 ends up where fx2x1 used to be, and vice versa. But if fx1x2 is equal to fx2x1, then nothing's really changed. You still get all of the same things are going to end up being equal to each other. So Sarah, that's kind of the connection to the Hessian matrix is if you have a C2 function, it's going to have this property. By the way, the fact that this is called a corollary is basically a theorem that kind of is a direct consequence of another theorem. So in this case, the fact that this result is true basically is something that immediately follows from this theorem being true. It's basically a special case of this theorem in the case where k is equal to 2. By the way, we have a special name for matrices that are equal to their own transposes. We could say if A is equal to A transpose for a matrix A, we call A symmetric. Symmetric because if we were to take a matrix that is equal to its own transpose, like 1, 3, 3, 5, for instance, if we were to look at every entry that's not on the sort of main diagonal, going from top left to bottom right, if we were to flip-flop what's up and to the right of this diagonal with what's down and to the left of it, like this, or for a 3 by 3 case, 1, 2, 3, 2, 3, 0, -5, -5, 9. Everything up and to the right of the main diagonal, if it matches up with everything that's down and to the left of it, we could sort of think of it has some symmetry to it, and that we could sort of fold the top right down onto the bottom left, and they would match up perfectly. There's some geometric symmetry going on. And so that's why we call a matrix that has this property a symmetric matrix. So in other words, if we were to take the Hessian matrix of any C2 function, it's always going to be symmetric, have this property to it. Any questions, comments, or concerns? So, y'all can go. I'm going to start this with 5 minutes left. We had 10 minutes. We jumped into the next standard. So that's going to be it for standard 9. I will say there's one question on the back page that basically asks you to find the third order partial derivatives of a function. I think that would be like a good practice question for just making sure you know how to find partial derivatives of every order. So I'll let you try that out if you're interested. Hope you all have a good rest of your day. I will see you all on Friday where we'll start the multivariable chain rule.